Good morning, everyone. Thank you all for joining us today. My name is Tony Sanfis. I am the technology manager for M4 Connect. And today we are hosting an online workshop, a webinar focused on maximizing pH accuracy. So we'll spend the next 30 to 45 minutes here discussing this topic and diving in deep to help ensure that you're getting the most out of your pH measurement technology. Just before we dive in real quick, today's webinar is being recorded. For all of you that are in attendance today, you will get a link afterwards that will take you to that download. We will also be hosting a Q&A session at the end of the webinar. So please feel free as we go through the next half hour or so. Submit those questions through and we'll take some time at the end to answer them. If we don't get to all of them, we will be following up with the Q&A sent out to everybody. So with that, we're going to go ahead and get started here and just walk through the topics that we'll be covering today. So the first thing is, the topic of the day, understanding accuracy, right? And I get this question a lot. How accurate are your pH electrodes, or what is the accuracy specification on your pH electrodes? And we'll touch on that, but I really want to focus on accuracy of the measurement. And the measurement is more than just the electrode itself, so we'll dive into that. We'll talk a little bit about choosing the right pH electrode for your application. As I'm sure you all are aware, there are multiple different styles of pH electrodes, industrial pH electrodes out there on the market. We'll talk about what you should be paying attention to when you specify or work with manufacturers to specify pH electrodes for your application to get you the most accuracy and longevity out of those particular electrodes. We'll talk about basic maintenance and calibration and storage. Those all play a key role in maintaining accuracy of your equipment. And then finally, we'll talk about the benefits of smart digital technology versus what we're going to refer to as traditional analog measurements, analog technology being the signal from the electrode to the transmitter, not necessarily the transmitter to the control system. So we'll spend some time talking about analog to digital technology and how that can be a benefit to you in maintaining accuracy. So again, I mentioned it earlier, measurement accuracy versus component accuracy. And oftentimes we get a lot of folks ask us, for those specifications, those individual product specifications for the pH electrode. And, I'll just state a standard Connect industrial pH electrode has an accuracy of about plus or minus 0.02 pH. And you may be thinking, well, that's excellent, that's great, which it is, but it's more than that when you talk about measurement accuracy. Those pH electrodes need to be calibrated every so often. The calibration buffers also have an individual accuracy statement listed on the buffers as well. The Connect Calomat buffers are plus or minus 0.02 pH as well. If you're conducting a 2-point calibration, those can be added up. So it's very important when we get into specifying the electrode for a specific application, when we get into cleaning and calibration, that all these things are covered well and thoroughly to ensure we're maintaining accurate, highly accurate measurement accuracy when we are measuring in pH in our process. The very first thing that I like to start with is the electrode itself. And at M4 Connect, you can see we have multiple different measurement membranes, pH measurement membranes, depending on the technology that's being used. We primarily at M4 Connect deal with combination electrodes. So when we talk about a combination electrode, there are three main components to that electrode, the most important of which is the pH measuring membrane. That is the sensitive membrane. On this particular electrode, it's a glass bulb that is sensitive to hydrogen ion activity. That is the measurement membrane. The second component is the reference system, and that is built into a combination electrode. We'll talk about the reference system in more detail here in a minute, but it plays a very, very important role in specifying what type of electrode is going to work best in your application. And then the third component of that combination electrode is an internal temperature detector. Temperature plays a key role in pH measurements. Combination electrodes have that temperature element built into them. So we're going to kind of dissect those components and talk specifically, when you should use certain types of those components versus other types for your application. So when we talk about the measurement membrane, you see here on this slide, right? We at M4 Connect have 4 main recipes of glass that we use on glass pH measurement membranes. The first one you see there, our most common, the alpha glass. It is a medium impedance. We call it a universal glass. Very good for standard industrial applications. It's also fluoride resistant. So if you have fluorides within your process, the alpha glass recipe that we utilize, it works very well. If you're familiar with the Connect model of sensors, that is our SE554, our SE571, our SE560 utilizes that alpha glass. So again, medium impedance, kind of universal for a number of applications, and fluoride resistant. The next most common glass that we utilize is our omega glass recipe. This glass handles really, really well at high temperature. So applications where CIP, clean in place, or SIP, sterilization in place, may occur, the omega glass works really, really well, and it has it's very robust, and it has a long life in those type of applications. Our SE555 at M4 Connect utilizes the omega glass. We can have that sensor remain in place during a CIP or an SIP process, and that glass membrane holds up really well to those extreme conditions. Again, universal across the pH spectrum, so 0 to 14, it works really well, but we tend to go towards that omega glass in applications where we're going to see CIP or SIP cycles at a frequent rate. The next one there, our Sigma glass. This is kind of our entry point, if you will. So standard water, wastewater applications. We utilize our Sigma glass on, for instance, our SE515, which is a water, wastewater MemoSense electrode. Very good in those applications. We'll talk about the specific reference junction in that SE515, but that model sensor utilizes our Sigma glass. And then finally, from a glass electrode standpoint, our H glass. H glass is utilized on the PLH93 model sensor from M4 Connect. Very, very good, withstands very high temperature and high pH values. So those hot alkaline processes, we see those often within the paper industry, for instance. The H glass handles those particular applications very, very well. And then, of course, we have other non-glass measurement membranes within our product portfolio. The two that you see there at the bottom are very unique. The first one probably being more common than the second one. And the first one is ISFET technology. So ISFET stands for Ion Selective Field Effect Transistor. I've got an ISFET sensor here. I'll just leave the watering cap on, but it is a plastic peak-bodied sensor, and the measurement membrane, as opposed to being a certain recipe of glass, is a semiconductor chip. So that field effect transistor, that transistor is sensitive to hydrogen ions, just like the glass membrane would be on a glass electrode. And it's very, very good in applications, maybe it's food and bev or pharma applications where glass cannot be present. That semiconductor chip, that transistor, is measuring the hydrogen ion activity. And then finally, the last measurement membrane that we'll discuss a little bit is what we call a glass steel enamel electrode. This is a non-glass sensor. It's made of enamel, like the enamel on your teeth. Very chemically resistant, very robust technology. And that enamel utilizes a hydrogen ion sensitive band for measuring hydrogen ion activity within a process. So these particular electrodes have benefits because they can be left dry. Again, they're very robust. They can also handle CIP and SIP cycles. So it's very important when looking at the characteristics of your process, starting with the pH measurement membrane, what type of measurement membrane are you going to select? Are you going to select glass and are you going to select non-glass? And if so, what specific type or recipe is going to be most beneficial in your process for gaining accurate results? Next, when we talk about the reference system, again, so I mentioned, three main components. We've got our measurement membrane that's sensitive to hydrogen ion activity. Next, we have our reference system. And that reference system is what's going to electrically couple your process that you're measuring to your reference electrode that in a combination electrode is housed inside the sensing body. That pathway of maintaining that electrical connectivity is what's referred to as the junction or the diaphragm. And there are multiple different types of junctions or diaphragms that are utilized on industrial pH electrodes. Here on this slide, I've got really the four most common that we utilize in the vast majority of our applications. And we'll start with the ceramic version junction, or diaphragm, if you will. A ceramic junction sensor, if you put it under a microscope, those ceramic junctions are porous, just like the pores on your skin, and they allow an electrical coupling between the process that you're measuring and your reference system. So your reference system has that reference element, it has a reference electrolyte, and that has to be electrically coupled to your process. In that pathway, that bridge, if you will, is through the junction. Ceramic is very nice because ceramic is harder than steel, believe it or not. So what that allows us manufacturers to do is internally pressurize the reference system, that reference electrolyte, to force that electrolyte out of those pores at a certain rate to make sure that we're not getting contamination or blockage there. Again, you want to maintain that electrical connection to get accurate measurement results, and ceramic holds up very well to those hot, extreme processes. Of course, ceramic is porous, right? So there's small pores on there, and just like the pores on our skin, we want to keep those pores clean. So if you have an application where those pores may plug up, we would look at something like an open junction electrode. So this is our SE554 model from Conic. This is an open junction electrode, the junction being located right above the measurement membrane, the glass bulb here on this particular sensor. And although they're small, they're still much larger open holes than the pores of, say, a ceramic junction. So this particular type of junction is well suited in an application that's going to have fine suspended solids or particulates that may plug those ceramic pores. We'll talk about it here in a minute, why this particular electrolyte looks different than that of a ceramic junction sensor. But again, it's the same composition. It's the same purpose, that open junction, as the porous ceramic. It's serving as the bridge to electrically couple our process to our reference system. Moving over to the third one, PTFE. PTFE or Teflon, it serves very, very well in applications where you may have oily coatings or processes that can, cover the pores of the ceramic junction or plug up even the open junction and get inside that reference system and contaminate at a fast rate. That PTFE is a natural wicking agent. So if we have oily applications, that will just wick right off of that junction and aid in keeping that pathway or that bridge clean. And then the last one is our ground glass sleeve. Again, we utilize that on our SE515 MemoSense sensor. That glass sleeve is a nice protective agent while still maintaining coupling of the reference system in the process. Very good in standard water, wastewater applications, outfall type applications where you may have some particulates, some algae buildup, but not necessarily a high amount of suspended solids present or oil located in your process. The ground glass sleeve junction works really well. When we move inside, so we just talked about our junction, our bridge, if you will, of electrically coupling the process to the reference system. When we move inside to the reference element itself, this is what's maintaining a stable reference voltage when we're making a pH measurement. It's very important on what type you utilize. The most common on the market is a silver chloride reference element. And often, as with the case with our SE515 sensor, that is a silver wire with a silver chloride coating on it. Now, you want to ensure that that silver chloride reference element is in a clean, neutral electrolyte solution, and we'll talk about that here in a moment. But of course, over time, you are going to get process into that reference system just due to the general nature of a glass pH electrode and that junction. So what's important is protecting that reference element, right? Keeping it clean, keeping it in a neutral solution. That's where a double junction sensor, like you see here in the middle, really plays a role in maintaining highly accurate measurements, especially in harsher industrial environments. The double junction sensor from Conic, we call it a Silamid reference. It's actually a glass tube that is lined with silver and packed with silver chloride. That allows us to put a filter on the end of that glass tube, or another junction, if you will, and that protects that element. Once process comes in contact with that silver chloride element, you're going to get a shift in your reference voltage. It's going to poison and contaminate that reference system. So it's very important to protect that, and double junction electrodes aid in that. They aid in longevity of protecting that silver chloride reference. And then the third one that we have up here is actually differential technology, which we utilize on our enamel probes. So you may have noticed when I held this enamel probe up earlier, there are actually two different color bands on here. The first one is our measurement membrane that is sensitive to hydrogen ions. The second one is our reference element, our reference membrane. And this particular technology is sensitive to sodium ions. So the benefit here is we establish a reference based off the sodium or salt content in your process. So this sensitive band, this sodium ion sensitive band, establishes a very stable reference voltage based off the salts that are in the process. Again, you want to ensure that it's maintained and kept clean, but it establishes a very stable reference voltage using the process itself. So no junction on this type of electrode. We're using the process to develop that reference potential. When we talk about the glass style electrodes, and we talk about the different types of reference electrolyte and where those are going to be beneficial in your applications. The three most common are a gel style electrolyte in a combination electrode, a liquid electrolyte, and then a polymer. And it's important to note, folks, that each of these particular electrolytes from M4 Conic and Conic are made up of 3 mole KCl, 3 molar potassium chloride solution. They're just in different forms. We often like to standardize on a gel electrolyte. We utilize that gel electrolyte in our ceramic junction sensors. It's still, it's got some viscosity to it, but it's got a good flow. And when we internally pressurize that particular style sensor, that gel electrolyte flows out at a nice solid rate out of the pores of that ceramic junction. When we move to an open junction electrode, we have to obviously move away from a liquid or a gel that has more flowing tendency to it, and we have to polymerize that 3 mole KCl electrolyte. That's because we don't want that electrolyte to flow right out of those open junctions. So it's important, the different types, when you're specifying a certain junction and reference type for your application, it's just important to note the type of electrolyte that's being utilized. When we go to liquid-filled sensors, those are often utilized in applications with very low ionic activity, low ionic processes, like boiler water, for instance, and we're talking in single-digit microsiemens for conductivity values. They will leach out the electrolyte from the sensing element, so from the reference system. So a flowing liquid reference electrolyte is often utilized and recommended in those type of applications. At M4 Connect, when we specify an electrode, we kind of break it down into simple categories. You see here on this chart, if it's a wastewater application, we'll often lead with a ground glass sleeve and that Sigma glass style electrode like the SE515. That's not to say that the 555 and the 554, an open junction or a ceramic junction sensor, wouldn't work in a wastewater application. They absolutely would, but this just helps lead for the different types of membrane and different model sensors based off application characteristics. Again, as I mentioned, low conductivity solutions. So low conductivity solutions where you have no ionic activity taking place in the process, they tend to leach out that rich ionic activity in the potassium chloride reference electrolyte. So we would look at special sensors. If that's a gel filled sensor like our SE558, we incorporate reservoirs, KCl reservoir rings within that sensor to slow that leaching process down. If that application is real aggressive from a leaching standpoint, we would then turn towards something like a liquid-filled sensor and continuously feed electrolyte to that sensor to ensure that we've got a nice, clean reference system. And then the bottom two, of course, suspended solids. We already mentioned that. Suspended solids, it's ideal to look at an open junction electrode. We want to make sure that the junction is not getting plugged up. So suspended solids is fitted very well to an open junction style electrode. And of course, non-glass, if FDA requirements or pharmaceutical requirements dictate that no glass can be present in your application, you want to look at a technology such as ISPET technology or the enamel technology that we showed with the glass steel style differential sensor. So now that we talked about, the specifics of specifying an electrode, I want to talk about specifically best practices for cleaning those electrodes, right? So these electrodes do age over time. They have to be cleaned. They have to be maintained with calibration. And again, going back to maintaining highly accurate results, you want to keep in mind best practices when you go to clean and calibrate your electrodes. If you're operating in a very acidic process, we often recommend an alkaline, a mild alkaline solution to neutralize that acidic process off the pH measuring membrane. So it's a very good idea when you're cleaning the electrode to clean both the measurement membrane and the junction. And we always recommend to do that chemically as opposed to physically, especially on a glass electrode. You don't want to start being abrasive on that glass measurement membrane because you can build up a static charge, which is going to lead to inaccurate measurement. So acidic processes, it's a good idea to neutralize that acidic process with a mild alkaline solution. Let it soak, 15, 20 minutes. And then, of course, anytime during the cleaning process of an electrode, when you're done letting that sensor soak in the cleaning solution, you want to rinse with DI water, and then, if possible, store it in its storage solution. We recommend storing the sensor in a 3 mole KCl potassium chloride solution. We offer such at M4 Connect. And the reason being is, again, that is the same composition as the internal electrolyte, and that's going to keep that electrode at a very relaxed state if it's got the same composition on the inside as it does on the outside of the measurement membrane. For other processes, this is very common from a cleaning standpoint. We often recommend a diluted acid. Hydrochloric acid tends to work best, that 5 to 10% range from a dilution standpoint. Commercially, this is muriatic acid, right? You can buy muriatic acid at your general hardware store, but most facilities have some hydrochloric acid in the lab that they can dilute down to help clean their electrodes. And again, you want to make sure that you're soaking that electrode, both the measurement membrane and the reference junction, for a process of 20 minutes or less, and then rinse that acid off the electrode and then move it to a storage solution, a KCl storage solution, to help regenerate that sensitive hydrogen ion layer on that measurement membrane. For processes that contain proteins, again, we offer it's a diluted HCl solution, but it's mixed with a pepsin, and that's very good at removing proteins from electrodes. You can order this from any lab warehouse. You can order it from M4 Connect as well. So protein coatings on the measurement membrane and on the junction are well removed with an HCl pepsin solution. And then lastly, fats and oils. Isopropyl alcohol or acetone, ethanol is often utilized. Again, these are applications where, from a specification standpoint, maybe something like a PTFE junction that you're dealing with, you can utilize IPA or ethanol or acetone. Soak that sensor 15 to 20 minutes to remove any fats or oils that may have built up on the measurement membrane and on the junction itself. So just best practices, and we'll show the slide here, but we'll be sending this out in a follow-up. So I'm going to ask Seth here to switch to the screen, or to the camera screen, and just talk about best practices when conducting a calibration. So after we've removed that electrode from our process, and we've gone and cleaned that electrode the appropriate way and then moved it to a KCl solution, when we carry out our 2-point pH calibration with our buffer, it's always recommended, folks, to utilize fresh buffer solution. You see on these containers that we offer from Connect, we have a reservoir up here with a non-return little valve built into it. And that's to avoid cross-contamination. So it's very important to rinse in between your buffer and your cleaning solution when you conduct your calibration process. You want to also ensure, of course, that you do not have expired buffer solutions. I see it many times when I'm out in the field. Obviously, oftentimes we'll order very large quantities of these buffer solutions and we'll reuse them over and over. You want to make sure that you're using non-expired buffer solution and you're using the buffer, and then discarding it. You can do that for a few calibrations throughout the day, but you don't want to carry that over to the next day and the next day and weeks at a time using the same buffer solution. It's very important as well when you're using alkaline buffers that you want to make sure that after use of an alkaline buffer, you cover that container up. Simple CO2 from the atmosphere can get into that buffer and start to create carbonic acid, which will shift that value. And again, these buffer solutions have accuracy statements as well. So the more we use them, the more cross-contamination potential that's exposed there, the less accurate they are becoming, and the less accurate our measurement is going to be. So 2-point calibration is recommended. Ensure that you're cleaning in between each buffer solution. And of course, make sure you're storing the electrode in a 3-mole KCl storage solution. So we show that here on this particular slide from a storage standpoint, just some tips and best practices. I can't say it enough, you know, the 3-mole KCl solution is what we recommend. But folks, never, ever store an electrode dry, especially a glass membrane. That glass membrane that is sensitive to hydrogen ions is only sensitive to hydrogen ions when we have a certain layer that forms on the inside and outside of that membrane. We refer to that as a gel layer. That gel layer formulates when you have electrolyte on the inside of that special recipe of glass, and you have a process solution, an aqueous-based solution on the outside. So electrolyte on the inside, process solution on the outside, and we generate that sensitive layer that's sensitive to hydrogen ion activity. If we let this sensor store dry, that gel layer is no longer going to be present, and that sensor is going to become very sluggish. The same, I see it often, if you store a pH electrode, a glass pH electrode, in deionized water, just as we talked about in those low ionic processes, what's going to happen in that particular instance is your internal reference electrolyte is going to be leached out of the reference system through the junction. And again, you're no longer going to have an accurate pH sensor when you go to introduce that into your process. You'll see a bunch of crystallization because of the leaching of the electrolyte. Storing in DI water is a major, major no-no. So again, just to ensure accurate measurements, we want to make sure that we're properly cleaning our electrode, we're properly calibrating, rinsing in between, we're compensating for temperature, we're ensuring we're using fresh buffer solutions, and we're storing the sensor appropriately, preferably in a 3-mole potassium chloride solution. So those are the key components when specifying and maintaining a pH electrode, an industrial pH electrode that's going to lead to accurate results in your process. Now, all of those things can be applied to traditional analog technology, and I'm not going to dive into the specifics of analog technology, but just high level, what an analog electrode is doing is it is generating a voltage, right, based off hydrogen ion activity, and then it is transmitting that voltage from the sensing electrode, the sensing element, over a cable to the transmitter. That voltage is carried from the head of the electrode to the transmitter, and there are things that you need to ensure to make sure that the voltage that is leaving the electrode head on an analog sensor is the same as the voltage going into your transmitter. So this slide here on the left shows a standard combination analog electrode and a standard analog cable. Oftentimes you'll see analog electrodes with a potted cable. A cable that is integrated into the sensing element and has a number of leads. Those leads could be tied to the pH measurement membrane, the reference electrode, and the temperature electrode. But again, those are designed to carry the voltage that is generated by that electrode through the cable, from the electrode through the cable to the transmitter itself. So it's very important to maintain signal integrity there. Oftentimes amplifiers, preamps are utilized to boost that voltage, which is a small voltage from the electrode to the transmitter. If you're in an industrial environment and you have motors operating nearby, that can have an impact on that signal. So grounding is very appropriate for maintaining an accurate signal coming into your transmitter. Now, when we talk about a shift from analog sensing technology to digital sensing technology, we're still measuring a voltage, right? We're still calculating and generating a voltage based off hydrogen ion activity, but that voltage, that analog signal, is converted in the head of the electrode to a digital signal. And that's what you see here in the diagram, or the exploded view, if you will, on the right. This is a MemoSense smart digital sensor. We see an electronic chip on the head of the sensor and an electronic chip on the cable connection. MemoSense utilizes an inductive coupler system so that power and digital data is transferred inductively, so there are no metal contacts there. That's a major benefit, especially in environments where we're gonna, obviously be exposed to moisture, humidity, wet environments. They can impact that signal transfer. That goes away with inductive technology. But just bare bones basic, what we are doing is an A to D conversion, and now we are transmitting a digital signal out of the head of the sensor back to our transmitter. So things like cable runs, where we need to limit that distance between the sensing element and the transmitter to ensure that voltage on an analog loop is the same coming out of the sensor as the voltage going into the transmitter. We had to shorten that up to maintain that accurate reading there. That really goes away with digital technology. The MemoSense technology, for instance, is carried on RS-485, so we can go 3/4 of a mile with that digital signal from the sensing element to the transmitter, and it's nice and clean. It's the same signal that's leaving the head of the sensor as the signal going in to the transmitter. So digital technology really cleans that signal up. But the other benefit is, now that we have a chip, a microprocessor in the head of the sensor that is primarily doing an A to D conversion, we can now store data in that sensing element. So data can be stored in the head of the sensor, and understanding that data is going to help you from a measurement accuracy standpoint. So the last 10 minutes or so, we're just going to dive into that data, what's available to you with the MemoSense digital technology. So here what you see, and I'm actually going to ask Seth to change the camera again, and we'll just show you in real life with this technology. Here what you see is the key parameters of a glass pH electrode that we're continuously monitoring with a MemoSense digital sensor. These are things like slope, 0 point, glass impedance, response time, and sensor wear. Those are all things that with analog technology, you need to pay attention to the specific voltages and specific impedance values to understand, are you getting maximum accuracy out of your pH electrode? Because digital technology is constantly monitoring these things and storing adjustments in the head of the electrode, we can now continuously look at those variables and predict things. We can help you determine when you're going to clean the electrode, when that electrode needs to be calibrated, again, ensuring maximum accuracy out of that electrode. So here you see a full diagram, a great brand new sensor, a great looking sensor network diagram. But as that sensor ages over time, this diagram is going to move inward, starting with slope value. Slope value, a theoretical slope as defined by the Nernst equation for a pH electrode, is 59.16 millivolt at 25 degrees Celsius. That's going to change over time as that electrode ages. Our diagnostics as a standard, we tie that between 80 and 103% slope value, that percentage being of a perfect 59.16 millivolt. That's often an acceptable range. But if you're measuring in a highly accurate process, you might want to tighten that range up. And the digital monitoring technology allows you as the end user to freely do that. But again, slope value is one that's very important and will age over time. And that aging needs to be compensated for. That's done via the calibration process. The other one that's specifically tied to the calibration process is the sensor 0 point. Right? So again, from an accuracy standpoint, you want to make sure that you're continuously monitoring the 0 point of the electrode. So we talked about the reference system. That reference system is designed to be a neutral pH value, right? So a pH value of 7 inside the reference system of the electrode. If we put that particular sensing element into a neutral process, we would expect that pH electrode to be generating somewhere around 0 millivolts. Your 0 point is the voltage that sensing element is generating in a neutral solution. And again, that's going to change over time. As our process will work its way into that reference system, it's going to shift that neutral value of that reference electrolyte in that reference system. And we need to make sure we're paying attention to that. The digital technology allows us to continuously look at that 0 point, but it's a good idea to keep that 0 point within a range of about plus or minus 30 millivolts per unit. So plus or minus 30 millivolts. As that starts to shift over time, you're going to experience sluggish results, and oftentimes you may need to rehydrate that internal electrolyte by soaking it in a potassium chloride solution and then recalibrating your electrode. Another key important diagnostic is glass impedance. Glass impedance is something that we're continuously looking at on the MemoSense technology, and where it's beneficial for you all from an accuracy standpoint is glass impedance can be tied to an indication of buildup or contamination on that measurement membrane. It can also be an indication if your sensing element is not fully submerged in your application. So from an installation standpoint, we need to have that measurement membrane, and we need to have that junction fully immersed into the process. If it's seeing air, you're going to see that glass impedance value be jumpy, if you will, and go up and down at a fast rate. If you're starting to see coating on the electrode, you're going to see that glass impedance value climb up. And then finally, if your glass electrode breaks in your process, you're going to see that glass impedance value completely drop out. So that's a good diagnostic to continuously look at. Response time of the electrode, we monitor that over time during the calibration process, and that's really the amount of time that the electrode needs to settle out during that calibration process. So when does that temperature reading become stable? When does that voltage reading become stable when it's moved from one buffer to the next? It's continuously monitored in the MemoSense diagnostics. And then finally, sensor wear. Again, these electrodes, they wear over time, particularly when exposed to extreme conditions. We talked a lot about CIP and SIP applications. Very high temperatures will wear on an electrode, just like very high or very low pH values will wear on the measurement membrane of the electrode. So digital technology allows you to continuously monitor those extreme conditions that the electrode's been exposed to, apply that to an algorithm that then generates a sensor wear percentage and also a lifetime remaining calculator that ensures that you have a highly accurate electrode in your process. As that sensor wear increases over time, obviously you'll need to maintain that electrode and then eventually replace that electrode to ensure that you have a highly accurate measurement. So With that, we're going to conclude, this portion of the workshop and switch it over. We're right at the 45-minute mark, but we're going to take a little bit of time just to answer a few questions. And then, as I said, we will be sending out a recording to everybody that attended today's webinar, along with all the questions and answers that were submitted today. So I want to thank you all. I'm going to mute it right now and ask Seth to read off a couple questions, and we'll take a few moments to answer those while we're online today. Yep. So one of the questions that came in was specific to different junction types, particularly ceramic junction versus ground glass sleeve, and when would you use the different versions. The ceramic junction sensor, and I'm talking in sensor model here, the Knick model SE555 utilizes a ceramic junction sensor. We utilize those often in applications where we're going to see extreme elevated temperature. So those CIP and SIP applications, so industries such as pharmaceutical, food and bev, where they're going to clean in place or sterilize in place their lines, a ceramic junction sensor is ideal. The ground glass sleeve offers a higher surface area and more direct access to that reference system. We often utilize that in wastewater type applications. So maybe not extreme temperatures in those applications, more ambient type temperatures, but it allows direct access to the reference system as opposed to the porous ceramic, which allows us to internally pressurize the reference system and expose the sensor to extreme conditions such as CIP and SIP cycles. We had a couple more questions just come in. I'll answer one last one here, and then we're going to conclude the webinar. The question that came in is specific around calibrating in order of the buffers that is utilized. It often doesn't matter the order that you utilize, but I highly recommend best practice to start with a neutral buffer 7. Set your 0 point and then rinse in between and move on to your next buffer solution. It's best practice to try to bracket your expected measured value. What I mean by that, and you'll see that in the guide that's sent out as well, if your expected measured pH value is that of a pH 5 or 6, start with a buffer 7 and then move to an acidic buffer 4 and bracket your expected measured value. If you're more on the alkaline range, replace that buffer 4 with, say, a buffer value of 9 or 10. So want to thank everybody for joining today. Again, we had a few more questions come in, but I know we're up on time. I want to be respectful of everybody's time this Thursday. I wish you all a great weekend. Thank you once again for attending, and look for that email with the recording of the webinar and all the Q&A. So thanks, everyone, and take care.